So our first speaker of the day is Hans, who will be talking about MaxSAT as well, mainly preprocessing for MaxSAT.
Yes. Good morning, everyone. So I will be talking about proof logging for MaxSAT preprocessing, and this talk is based on a joint work with all these people listed here. So Andy, Yonghyun Tan, Jeremias, Matti, Magnus, Myren, and Jakob. So we have a paper that will appear on ITSCAR this year. And in the paper, we take our standalone MaxSAT preprocessor, which implements something like more than 15 preprocessing techniques for MaxSAT, and we add proof logging for all of those. And we also have like formally verified end-to-end proof logging for all these techniques. So the outline of my talk will be this. So I first talk about MaxSAT and preprocessing, give some preliminaries for this topic. Then I talk about proof logging for MaxSAT preprocessing in general level, and then I give practical examples for what are the techniques actually doing and how we actually prove them to be correct. So I guess you have already all seen MaxSAT this week. So we have CNF formula, and then we have objective function. And we need to satisfy the CNF formula and minimize the value of our objective function. And here we have an example instance. And there are now 3 solutions to this MaxSAT instance. 3 assignments that satisfy our CNF formula. So we can assign x1, x2, and x3 all to true. And then we have to assign x4 to false. And the other 2 solutions assign all of these 3 variables to false. And then we can assign x4 to either true or false. And the objective function gives us cost for each of these 3 solutions. And we can here see that tau2 got the smallest cost, the smallest value for the objective function. So it's an optimal solution for this instance. But for preprocessing, we also actually need different form of MaxSAT. So I'll need to talk about soft clauses and hard clauses. Even though Jeremias said we are like trying to debunk them, so they have nothing to do with MaxSAT. But the MaxSAT instances have soft clauses and hard clauses, and our preprocessor actually does preprocessing on the soft clauses and hard clauses before converting the instance. So this is what I will call WC in a form of MaxSAT. We have a set of hard clauses, we need to satisfy them all, and a set of soft clauses that are associated with integer weights. And the cost is now, solution is now something that satisfies all our hard clauses, and we want to minimize the total weight of unsatisfied soft clauses. And there is this standard conversion, how we get from this clause, MaxSAT with soft clauses to objective-centric representation. So for each soft clause that has more than 1 literal, we introduce a new variable to the clause and make the clause a hard clause, as is done here. And then we introduce a new soft clause that has now negation of this new variable we introduced to the soft clause. And the claim is that this instance now has same optimal cost. And it's quite obvious when you think about it for a while. So if we falsify this, we need to set x4 to true, so we will falsify the soft clause. And if we satisfy this, we can set x4 to false, so no cost there. And this is now basically equivalent to saying that we have a CNF formula and objective function, like I first presented. Okay, then about preprocessing. So the idea is that we have standalone preprocessor. So we take our input instance, preprocessor does some magic, and it reformulates the instance to an easier instance for our MaxSAT solver. Then MaxSAT solver solves the instance, and we get solution to our preprocessed instance. And now, of course, we are actually interested in the solution of our original instance here, not our preprocessed instance. So we need to be able to reconstruct a solution to our original instance from our solution to our preprocessed instance. And our preprocessor is able to do this. How it does it in practice is that in addition to producing this processed instance, it also writes a separate file that has something we call reconstruction stack. And then given this optimal solution on reconstruction stack, it is able to produce this solution to our original instance. Okay, that's about the preliminaries. Now let's go to proof logging part. So what we do with proof logging is that we verify that what our preprocessor does here is actually correct. So we verify that our input instance and output instance of preprocessor have the same optimal cost. And now actually you might have this relevant question, what about this reconstruction? So if we verify this step here, and we have MaxSAT solver that produces also proof, we can verify this step here, but it's not enough, right? Because we are not interested in the correctness of this, but we are actually interested in correctness of what we get here. And now I claim that we don't need proof logging here. It's sufficient to add it here. And the reason is that when we have verified the equi-optimality of our input instance for our preprocessor and output instance of preprocessor, and the optimal solution for our preprocessed instance, we can verify that this reconstructed solution is solution to our original instance, and it has the cost equivalent to cost of this here. And now this is sufficient for showing that this is actually also optimal solution for our original instance. So we can think about reconstruction as some magic box that does stuff, and we can still verify that we got the correct optimal solution to our instance. So I hope this convinces that it is, like, in principle sufficient to add proof logging to that direction. Okay, so then what is now different if we compare to other proof logging things we have seen? So one thing is that we actually convert MaxSAT instances to PBO, not in our preprocessor, but it's all implemented in proof checker side. And we have formally verified conversion, so you don't have to trust that the preprocessor does correct conversion from MaxSAT to PBO. And yeah, the conversion is in a sense trivial, so we convert MaxSAT to objective-centric view. And then there's this, because MaxSAT is like subset of PBO, there's trivial conversion from clauses to 0, 1 linear inequalities. And another difference is that now we don't have answer we are verifying, but we have output instance we are verifying here. And so what exactly the verifier does? So we check that when the verifier has got to the end of the proof and is happy that everything we did is correct, it reads the output instance and verifies that the constraints in the core set of the verifier are exactly the constraints you get when you load the output instance, and that the objective functions are exactly the same. And then you have verified that output instance and input instance are equi-optimal. So some characteristics of what is now how this is somewhat different from other proof logging things we have seen. So if we compare to proving optimality, now we can't add any objective improving constants, even though our preprocessor can find solution of the instance, because that would break equi-optimality. So we need to actually come up with some different techniques of proving things that are also done in MaxSAT solvers, because we can't have these objective improving constraints. Then we are mainly adding and removing core constraints. So all the time, the instance of the preprocessor matches to the core constraints of the proof. And then we are using quite heavily redundancy-based strengthening and check deletion rule. And we also update the objective function often. And because of we are adding and removing core constraints and using redundancy-based strengthening, it has some, like, it affects our performance of checking the proof, but we are still, I think in most instances here you see that we get less than 100 times overhead for the checking the proof. So it's not that bad, but of course it could be better. And so this is actually the time for running both VeriPB and CakePB for checking the proof. And okay, I also already mentioned that we are first preprocessing with the soft clauses and then with the hard clauses. So here are actually 5 stages of preprocessing we are having. And so first we load the formula. And at this stage, the proof, of course, loads the formula and has exactly the pseudo-Boolean presentation of that MaxSAT instance. Then we preprocess on the WCNF with the soft clause, and here actually what happens is something that makes it, well, makes at least the implementation of this a bit more annoying, because there is no trivial correspondence between it. So there is no trivial function to map this MaxSAT instance of preprocessor to the instance of proof. So there is, in a sense, like every constant in preprocessing corresponds to something in proof, but there are cases where the pseudo-Boolean proof has these extra variables in some of the constraints, and it's not trivial to see from here which constraints actually have the extra variables, because we might modify the soft clauses. But then we convert the instance to objective-centric view, and after this, the preprocessor and the proof have pretty much the same instance. So I have asterisk here, which means that the variable names might be different at this point. But otherwise, all the constraints of the preprocessor correspond or are like exactly equal to a corresponding constant in the proof. And that is true until the last point when we remove the constant from the objective function, because we are producing WCNF output file which can't have any constant. And after we remove that and rename the variables, we again get that our preprocessed instance is exactly the instance we load when we convert it to our preprocessed instance. WCNF is exactly corresponds to the core constraint of that the proof has. Okay, so now we go to the interesting part, like what the techniques are in practice and how we prove them. So I'll say something about each of these 5 stages you saw. So first is initialization, and here's just an example of what it might look like. We got input MaxSAT instance, it has hard clauses and soft clauses. And for all hard clauses, we simply convert them to PPO constraints. If the soft clause has only one literal, we don't convert it to any constraints, we only add it to the objective function. If soft clause has more than one literal, we need to add this new variable and add it into the objective function. So after initialization, we might have something like this. So preprocessing with soft clauses. Here's an example of technique we are running. So we remove duplicate clauses. And to make this interesting, we have now duplicate soft clauses. And when we look at this, it's obvious that we can replace these two with this one soft clause that has weight the sum of these two. But now if we look what we have in the proof, we don't have duplicate constants here because we added these new variables. So at this point, to prove that we can actually do this and do it in the proof side, we need to get a bit creative. And what we can do here, so in a sense, these are equivalent, but these are actually not, because there might be solutions to the instance that if you satisfy these, you might actually set these to different values. So first thing we do in the proof is that we make P1 and P2 equivalent. So they are not equivalent in any solution, but they are actually equivalent in every optimal solution. So we add these constraints that encode that equivalence, and we need to do redundant-based strengthening because this is not implied by the formula. This is strengthening the formula. And we can use witness that assigns the variable in the objective function to 0. So
is there a reason why you're assigning it to 0 and not? So the natural thing for me would be to assign it to be 1. I can see that to 0 would also work, but
yes,
because the thing you want to do is without loss of generality, they're equal. So I just assign one of them the value of the other.
yes,
and then all
I
your
think
proof
that
obligations would disappear,
also work.
I guess.
The objective function. Yes, I guess
the
it
objective
won't be
might
trouble because you
get
get this negated in the left-hand side.
To guarantee that your objective doesn't increase.
Yes.
Yeah, okay, no, so probably mapping to B1 wouldn't work. Which is okay.
Yes.
Yeah, because you want to say that you assign both of them to the smallest of the two, basically.
Yes.
Yes. Okay.
So after this is done, we can actually remove this other constraint. It is now wrap with respect to what we have like other constants here. So this other constant and one of these implied.
You mean like check deletion?
Yes, yeah, it's check deletion. Yes, here. And yes, these are added to the core. And then we can also update the objective function. So because of these two constants, this is equivalent to 0. So we can add the objective function. And now we have actually removed this b2 from everything else except these two constants we added. And finally, we can remove these two constants, and there again check deletion, and we need to use a witness that sets the b2 to 0 and 1 for the other, but because b2 doesn't occur anywhere else, it's kind of trivial to remove these at this point. Yeah. So that was the example of what we do with in the first phase. So then the conversion to objective centric. Otherwise, we don't really need to prove anything at this point. We just add the object new variables and add some mapping that we know which max free variables correspond to which variables to prove. But there's one case which is different. So we might end up in a situation where preprocessor has unit clause that is soft clause, but in the proof side we have constraint where we have added this variable at the
Question from Jakob on the previous slide. Sorry.
Okay.
Don't you need a new fresh variable to be equal to both B1 and B2? Or how do you deal with the witnessing over B1 and B2?
At which point would the witnessing be?
The witnessing is the 2 star indented lines. There's the witnessing, right?
Yes. We don't need another variable. So at this point, witnessing B1 to false. So we get proof application from here and here basically. And if you falsify this constant we are adding, it implies this one. And then the other constant, if you falsify this and
You already have that B2 is false, so that either x1 or not x2 is true.
yes,
So the other one is okay.
yes.
So Jakob says if you set them to 0, then the soft clauses turn hard, don't they? He thinks you should be setting your witnesses to 1 in the example.
Oh, that depends. Like, if you have, depends on which polarity you actually introduce this new variable. So if you add here negation and here negation, which is I think what VeriPP actually does. So it adds negations to the objective function. Then you would witness them to 1, right? But
Jakob is happy.
yes,
So we should
yes.
move on.
And important is you need to decrease your objective, right? So you have to set them to 0. If you
Yes. So let's get this example back again. So how this might happen is that we got a soft clause that is not originally unit clause, and then we remove some literal from it in the first preprocessing phase. So we might end up with this, and then there is in PBO instance constant like this. And to make the preprocessor instance match exactly to what we have in the proof, we want to remove this P and have negation of x there instead, I think. And how we do this? In this case, we introduce constant that has both of these negated, and we use witness b to 0. And again, we get proof obligation from here, but if we falsify this constant, we are adding the satisfied constant, so we are happy. And the objective function doesn't get worse. And after this, we can add to the objective function the weight times minus not x minus weight times b. And this is because these two constants actually make x equivalent to not b. And after this, I can remove both of these constants and we are happy. Yes.
And does this happen? I thought that if you have a unit clause in the input file, that B doesn't add the
Yes.
blocking method.
Yes. So when this happens is that we had a soft clause that wasn't originally a unit clause. And then preprocessing might remove some literals and we end up with this situation. And yes, this is what I meant, that there is no like exact correspondence, because if we have that unit clause in preprocessor, we don't know basically if we have, it doesn't directly, anything doesn't directly tell us if there is like this in the proof or if there is only the unit clause. So we need to remember what have been done before. But okay, so let's get some like actually preprocessing techniques. So this technique basically you got two variables or two literals, and setting now L1 to 1 and L2 to 0 satisfies all clauses where L1 and or L2 appear in. So because these are supersets, so we can fix them this way and we don't remove any solutions. And if these don't appear in the objective function, it is also, we are not doing anything unsound. So now again, the question is, how do we prove that this is correct? In very PP. And if we introduce constants that say L1 is greater or equal 1 and not L2 is greater or equal 1, with witness L1 to 1 and L2 to 0, then we are happy because this witness now satisfies everything it touches basically in the instance. And because L1 and L2 don't appear in the objective function, that's also fine. And after we do this, we simplify the constant database, so we can remove every constant that there was because they are now satisfied because of these two constants. And then we can finally delete this constant we introduced, and then the variables have disappeared from the instance. But let's make this case a bit more complicated. And now, same situation as we had, but now we have the literal that appear in the objective function. And so there's now L1 and L2 with additional detail that L1 has coefficient that is less or equal to the coefficient of L2. And now what this means, if you think about all the assignments L1 and L2 can get, so we know that if we assign L1 to 1 and L2 to 0, that's always a satisfying. We always get a solution. But then we also now need to look at the cost of the solution. And because of this condition here, we have the coefficient of L1 is not more than coefficient of L2. We actually know that in these two cases, the cost of L1 and L2 is not better than we get here. So whenever we get a solution that says something like this or this, we can start this solution here. But of course, we can't set the same thing from here because, well, we don't get better solution from going here to here. So in this case, we fix L2 to 0, but nothing else. And again, the same witness actually works. So it satisfies everything it touches and yes, so compared to falsifying this constant, we are adding the objective function, doesn't get worse. And now we also need to remove the L2 from the objective function. So additional step here. But otherwise, it's similar than before. Yes.
Just to simplify the constraint database.
Yeah.
That actually look like in the proof.
In the proof. So it's check deletion. So for every constant here, you use check deletion rule, and I think in this case, I don't remember how it is currently actually implemented, but VeriPP can auto-prove this because you have this constant in the
I mean, I
database.
can
So-
see maybe that you could introduce all the simplified constraints by row, but if your constraint database was really large. It just seems odd that you would then delete L2 unless you've actually logged all the simplified constraints already. Otherwise, you're no longer going to get the simplification from unit propagation.
I'm sorry, say again.
So you're deleting L2 after you've done this.
Yes.
So you must somehow have the simplified constraints in the proof log. Have I understood that right?
Yeah, so the simplified constants don't have literal L2 in them, right?
Yes.
So we remove them. So so this is actually like we don't simplify this constant away before the last step, right? So
yeah,
we remove everything else where we have L2.
Okay.
Oh, yes. Did that answer the question?
Maybe. Anyway, it's fine. I'll let.
Okay. So next technique is hardening. And what that means is that we find a solution with the cost, and then if our objective function has some variable with coefficient greater than our cost, we can fix our variable to not incur cost in any solution. Right. This is simple. And if we would be proof-working MaxSAT solver, we could use objective improving constants here. So when we find the solution, we VeriPP introduce constant that value of objective is less or equal to this UB mean -1. But we can't do this here, so we need to do something else. So to be able to fix this e to 0, we are using the solution we found as a witness. So it obviously satisfies everything in the database, and because the coefficient of our b is greater than the cost of the solution, also we are happy with the objective function. Okay. So now let's get to most interesting technique I included here. So something we call label matching. And if our instance has clauses with C or BC and D or BD, where BC and BD are variables in the objective function that have the same coefficient, and C or D is tautology, and this BC and BD don't appear in other clauses. Then what we can do is that we introduce new variable that replaces BC and BD. And the new variable takes coefficient W in the objective function. So intuition why this is correct is that if this is tautology, we never want to set BC and BD true at the same time, because that would be, we can always set one of them to false and get better cost. And now this BCD variable basically same as BC or BD. And it is in a way implicitly encoded in here. Okay, so what does proof for this technique look like? So first, because C or D is tautology, we can assume without loss of generality that we have literal L in C and not L in D. Well, if C or D wasn't tautology itself, but that never is the case in our preprocessor. So the first thing is that we introduce not B or not BC or not BD as a clause. So it basically says that we don't want to incur cost in both of these variables. And we can now use as a witness mapping BC to not L and BD to L. So the witness definitely satisfies this constraint because it has two opposite literals. And if we think about these other proof obligations, the witness also satisfies those because C has literal L. If it now has not L, it is satisfied, and same for literal D. And also objective function condition is satisfied because falsifying this is worse for the cost than that witness. Okay, then we introduce this BCD variable, and we basically set it equivalent to the sum of BC and BD. And because we have this constraint that says that BC plus BD cannot be true, this is possible. So after this, we update the objective function. And because we have this constraint, this is sound. And we can introduce our new constraints to replace our old ones. They are now wrap. So basically follows from this and And then we can delete the original constraints, and then we can use the witness, which is PC to not L and PD to L for both of these deletions. So to see that this is correct, so definitely we satisfy the constant we are deleting, but there are also other proof applications, and it's not immediately obvious that this works, I think, but so let's see. We basically got proof applications other than the constants that we are deleting from here, right? And here. But this is satisfied by that witness, it's easy to see. And then, why is this satisfied? Well, it actually comes from if you falsify this constant we are deleting, then you actually would propagate BCD to 1 because we have constant C or BCD. And then this is actually satisfied because this makes the right hand side also 1.
So your actual definition of BCD, is that going to be technically like two reifying constraints with BC plus BD is greater than or equal to 1, and you're just relying on the fact that they're not going to equal 2 because of your first constraint?
Yes.
Yeah.
Yes. And then we can delete the constants that encode this BCD. And finally delete the constant inserts here first. Okay. So we are almost done. So the final step is that we need to remove the constant from the objective function and rename variables because WCNF file can't have constant in the objective function, and variable names should match at the end of the proof. So basically, how we remove the constant, add hard clause, and that falsifies a soft clause, and add the weight, constant weight to the weight of as the weight of the soft clause. So that's it. And in naming variables, so what we actually do is that for each variable, we take some temporary name and reify it to be equivalent to our original variable name. Then we derive constraint in this that have these t variables and remove the original constraints and do the same with the objective function. And then we can do the same again and not intend to the variable names we want. Okay. Conclusion. So we added proof logging for our standalone MaxSAT preprocessor. It was more than 15 preprocessing techniques, and it seems to work quite well, even though performance might be better, but it's still good. And we have end-to-end formally verified proof logging with KPB with this. And actually, to our knowledge, this is the first practical tool for even verifying satisfiability in 2 ways. So that's all. Thank you. Any questions?
renaming variables.
Yes.
Could that just be a very heavy feature, really?
Yes. We,
We thought about it, but we like to write that down. But we don't need it, but it is now.
yes.
If there are more people requesting it, then it will be implemented, I guess.
I mean,
Was there any
we
pure
might
renaming
find it
going?
useful, right? To rename variables.
Plausibly, yeah. That's
But there was no really pure renaming going on anywhere, right? It was always merging them or.
Well, it wasn't the last step,
previous
was it not?
step seemed to be.
Just to make sure that
Yes, and
it perfectly matched
But the last step was.
this here.
There, that one, yeah.
Yeah, yeah, because when
Yeah,
VariPP
true.
reads MaxSAT file, it actually like it adds these B names for the variables it introduces, and we can't like make it introduce the same variable names for our output instance. So we need to rename everything.
Is this derived constraints with T variables? Again, is this a like pretty trivial thing? Are you just adding these definition constraints in? to
Yes,
eliminate- Yeah,
yes.
so it's just cut and paste.
And what is the issue? Basically that you cannot name your variables in WCN. Is this why this was occurring, or is it?
Yes, it's that, and it's, well, you can name them in WCN, but you can
But only numbers,
on
not
the number.
Yes.
Yes.
So we'd have to do a bit more work if we wanted to rename variables, because we'd have the coefficients to worry about as well. We have to make sure it all lined up.
That's a problem.
I mean,
It's just
it's not a problem, but
Yeah.
yeah, well. Is it just syntax?
syntactically copying all your constraints within the variable replaced.
Yeah.
And then obligations should all go away, I guess.
Yeah. Question?